Hello, my name is Jin-Young Kim, and today we are going to talk about quantum computer and its fundamental theory and how it works. Most of us will be familiar with the word quantum computer, but we might not exactly know the details and how it works. A quantum computer is a machine that uses special quantum mechanical phenomena such as superposition and entanglement to quickly solve problems that would normally require repeated substitutions over a very long period of time, mainly through a process of drastically increasing probabilistic prediction. From this talk, we will look at how quantum computers started, its fundamental technologies including qubit, superposition, quantum entanglement, and finally how quantum computers will be used in the future. To know more about quantum computer, it is essential to learn about the beginning of quantum computer. The first person who presented the concept of quantum computing is a well-renowned physicist, Richard Feynman. When he studied quantum systems in 1983, he argued that current computers are difficult to handle massive amounts of calculations, and using a new level of computing tools that mimic quantum systems will make it easier to produce results. Then in 1985, Peter Shor of Bell Laboratories introduced a series of microfactor decomposition algorithms using quantum computers in the world in 1995. In 1998, Isaac Chuang and other scientists created the first quantum computer that could be loaded with data and output a solution. Although their system was stable for only a few nanoseconds, it demonstrated the principles of quantum computation and proved the quantum computer's possibilities. Now let's talk about the fundamental theories of quantum computing. The unit of information on a classical computer is called a bit, whereas it is called a qubit on a quantum computer. A qubit is a two-state quantum mechanical system, one of the simplest quantum systems displaying the peculiarity of quantum mechanics. Examples include the spin of the electron, in which the two levels can be taken as spin up and spin down, or the polarization of a single photon. In a classical system, a bit would have to be in a one state or the other. However, quantum mechanics allows the qubit to be in a coherent superposition of both states simultaneously, a property which is fundamental to quantum mechanics and quantum computing. In a theoretical way, qubit can be expressed as Blow sphere shown in the picture. Blow sphere is a geometrical representation of the pure state space of a two-level quantum mechanical system. These qubits have two important features that make quantum computer different than classical computers. One thing is a quantum superposition. Superposition is a fundamental principle of quantum mechanics. It states that, much like waves in classical physics, any two quantum states can be added together and the result will be another valid quantum state. And conversely, that every quantum state can be represented as a sum of two or more other distinct states. Mathematically, it refers to a property of solutions to the Schrödinger equation. Since the Schrödinger equation is linear, any linear combination of solutions will also be a solution. Quantum entanglement is a series of non-classical correlations that may exist between two qubits. The entanglement can exist even if the two subsystems are spatially far apart from each other. If the value of one qubit changes, the value of the other qubit that is immediately changes. According to quantum mechanics, the state of two particles is not known until they are measured. However, the measurement determines the state of one system at the moment, which immediately determines the state of another system that is intertwined with that system. It seems that if information has moved from one system to another in an instant, with superposition and entanglement, quantum computers can share and manipulate vast amounts of information, exponentially more than today's classical computers. Also, quantum computers can store all possible solutions at once. From this, they are especially good at calculating things that has small input and output, but has almost infinite array of possibilities. However, due to its imperfections, it seems difficult that quantum computers to perfectly replace of what classical computers take part in. One of its imperfections is called decoherency. With current technology, the quantum composed qubit cannot be maintained for sufficient time, nor can it be prevented from being modified by the minor effects of the external environment. Also, when two types of computers want to get the result they want, the optimized intermediate process is different, and replacing all the functions of modern computers with only quantum computers shows very low efficiency. So in the future, quantum computer will play as an assistant role of classical computer. Many research teams, including Google, IBM, and university laboratories, are trying to develop a step further the quantum computers. It's trivial that this is an important time to determine the whereabouts of quantum computers. Let's look forward to how quantum computer will develop.